Okay, in this short video, I've introduced another regularization model, which will be is very popular and useful for variable selection. Okay, so basic setup. Actually, this lasso regression was proposed by the Robert Tibshirani. In 1996, okay, which is the author of our reference book. Remember our the author, one of the author in both references book is Robert Tibshirani. Okay, so this is the method proposed by this famous statistician. Okay, so the idea is very sort of similar to the ridge regression, but you only need to revise. So the regression we still use the least squares linear regression. Linear regression. Okay, but plus not the L2 norm. Here we added L1 panel mean loss. Okay, in other words, we just need to find the coefficients for each variable that minimize so we have the loss function for the for the linear regression is the design matrix times W minus Y. Okay, so this is the cost function for linear regression, but here we plus the penalizations for the L1 norm. Okay, so that's the goal of the lasso regression. Okay, here where this L1 norm, recall, it's just the summation of the absolute value. Okay, I from 1 to D. Okay, so instead of using the squares, here we're using the absolute value. You may think, does that even matters? Actually, it matters in the following sense. For example, the ISO first, let's talk about the ISO contour plot for this norm 1. For example, suppose our W is just W1, W2. Okay, think about what's the ISO surface for W1 plus W2 equals to 1. For example, in the first quadrant, so this is W1, this is W2. In the first quadrant, both quantities are positive, right? So you have the W1 plus W2 equal 1. So this is equivalent to W2 equals to negative W1 plus 1, right? So therefore you have a contour plot is a line here, right? It's a line here. Okay, so you have this sort of the diamond shape ISO contour plot. So if you have the dimension more than 2, you have you have a polytopes. Okay, for example, 3 dimensions. Suppose this is W1, W2, W3. So this is our ISO surface for the W1 norm. It's not the same as a L2 norm. L2 norm is the ISO surface is the circles, right? It's circles. So this is W1. This is W2. W2. Okay. So why? So then you may think, why does that even matters? Actually, this following plot shows what's the difference. Okay. So first, this red ellipse are the SO contours for the linear regression lines. So this is without regularization. This will be the minimization point. Recall that in the ridge regression, not only you need to minimize about the SO contour plots on the linear regression, you also have the constraints with the SO contour plots of the L2 norm on the W. So you need to minimize this first one, but with restrictions, you need to survive on the blue circles. But for the for the lasso regression, we need to minimize the contour plot of the linear regression space, but also you need to have your solutions on this diamond lines. Okay, so if you have the small lambda, so you give a small penalization, is close to the W, this minimizer here. But if you give more penalization, okay, so you will drag the solutions to the boundaries of these diamonds. But as you can see, a lot of cases that ridge lasso regression will drag the solution quickly to some axis, for example, the L2 axis. If the solution draws to the L2 axis, the W1 will equal to 0, right? So this 2 dot W1 equals to 0. So this indicates if we give the relative large regularizations, we can ignore, we can find some variables not important. So in this case, is W1 not important because the features of X1 give the weight equals to 0. Okay, so that's the rough idea. So the weight W1 gets to 0, and that's what we want to happen. So the weight we do not have enough fluence. And for higher dimensions, if your solutions goes to some vertex, okay, so you eliminate the other two variables, right? So if your solutions contour ellipse just intersect here, okay, so which means W1, W2 is 0. So you find the variable, variable X3 is important. W2, W1 is not important. If your ellipse surface just falls into this region, okay, then you can say yes. So at some time point, several variables will have the this regularization will force some of the weight dropping to 0. Okay, so that's the big ideas of the lasso regression. So for example, I'll give you another plot here. Okay, so each feature represents a line. So for example, we have, so this example we have you can think this is X1, X2, X3, X4, X5, X6, X7. So we have 7 variables, okay? Initially, if we give the small penalization, all the variable has non-zero constant coefficients. But if you increase the penalization, Okay, at some time point, for example here. Oh, you think, oh, x random variable, the features x4, x5, x6, x7, they all have the coefficient 0. Only non-zero happens at x8, x3, x1, x2. Okay, by doing so, we can eliminate the non-important features. And if you give more and more penalizations, regularizations, more and more variables will have the weight close to 0. So you can think here, lambda is a parameter, hyperparameter. That can be tuned by cross-validation. Cross-validation. Okay. So that's basic ideas about lasso regression. But another difference is between the lasso regression and the ridge regression is that lasso regression, there is no closed form solution. Lasso regression does not have closed form solution. Okay, so the algorithm to solve the solutions for lasso regression, you need to use some numerical algorithm. For example, we can use this gradient descent algorithm. Also, maybe the least angle regression. But you do not need to worry about details here about the descent algorithm. This is already implemented in a lot of Python package like a scikit-learn package. Okay. So that's one difference between lasso and the ridge regression. Remember, ridge regression we have the closed form solutions. For example, this is the solutions for the ridge regression, right? But for lasso regression, we only have the numerical solutions. We don't have that clean math formulas. Another note here, important note. When you apply ridge or lasso regression, okay, you should probably normalize the features first. Always normalize. For example, you have the features, you subtract from the average of that feature, divide by standard deviation of that feature. Okay, normalize the features. Before you apply. Lasso or ridge. Okay. I think this lecture will give the introduction of the lasso and the ridge regression. Thank you.